Okay, thank you very much. So this is a talk about privacy. It's a joint work with my students, Saide Nayati Bogwan, Nazanin Takbiri, and my colleagues, Dennis Kekel and Amir Humansad at UMass Amherst. So, Internet of Things applications are widespread nowadays. We are all enjoying the benefits of this application. That's good. It's improving the quality of our lives. However, there are concerns about the privacy of these applications. And the reason is that whenever we are using these applications, we are sharing our personal data. For example, when you are using a ride-sharing app, you are sharing your location data. Or if you are using a health application, you are sharing your health data and so on. So we have to develop mechanisms to protect the privacy of users in this kind of context. Now, one way to look at these problems is to assume that you have n users, user one, user two, user n. You are using, these users are essentially using these applications. And each user creates a sequence, right? So user one creates sequence one, user two creates sequence two, and so on. So a sequence essentially is the data of that user. For example, in the context of the location data, it's a location of the user at different times. So at time 0, time 1, time 2, the locations of this user, this gives us a sequence. So we have a bunch of sequences. And to protect the privacy of users, we might anonymize the data, for example, which means that essentially you relabel the data, right? For example, user 1 becomes user 5, something like that. So, and you can go even further and you can add a little bit of a noise to the data so that, again, to protect the privacy of the users. So we say we obfuscate the data. Now, even if you do all of these, a potential adversary might look at this anonymized data and might still be able to match these sequences to these users. How? For example, this adversary might have some, prior knowledge about these users. For example, the adversary knows the statistical model for, some statistical properties of the sequences for user one, and is able to identify the sequence for this user among all of these sequences. So that's quite possible. So essentially, the scenario that we have, we're trying to develop the privacy preserve mechanism in this kind of situation. So what you can do, you can assume a user U. So U is the user, and the data of the user, you can just show it by XU of 1, XU of 2, XU of 3, and so on, right? So this shows the time. So at time 1, time 2, time 3, and so on. So you have a sequence. First you do obfuscation. You can think of it as a noisy channel, right? Discrete memoryless channel, something like that. So essentially, you might change some of the data. So this is the obfuscated data, ZU, and of course you then anonymize it. And what the adversary observes essentially is this anonymized data. So the adversary observes this anonymized and obfuscated data, but tries to get information about the actual data that we have here. Okay, so that's kind of the setting. Now, one way to look at these problems that our group has studied in the past, and other groups also have studied it, is to have a model-based approach. So what do I mean by a model-based approach? Essentially, you assume a model, for these sequences. The easiest thing that you can assume, you can assume an IID sequence, right? Independent identically distributed sequence, right? For each user, you assume that you have a sequence of IID random variables. Of course, for different users, you might have different distributions. That's how the adversary might be able to distinguish these users. Or you can have other models such as Markov chain, which is common when you have location data. Usually people model location data using the Markov chain and so on. So you assume a general model. You don't make any assumptions about the particular probabilities, but the general model. And then you try to design this obfuscation anonymization in a way that you achieve something like a perfect privacy. So what do we mean by a perfect privacy? We mean when the mutual information between the information that we are trying to protect and what the adversary observed in the limit can go to 0 when the number of users grow, right? When n is the number of users here. So in this context, we can say we have perfect privacy. and we can kind of develop methods like that. So the important point is that you assume a model for the data, because to compute the mutual information, you need to do the you need to assume a model for the distribution, and you can obtain the results. I provide an example from one of our results here. Question?
Yeah, sorry, it's Predrag. Question for you. If you go back one slide.
Sure.
So when you say n goes to infinity, you imply many users, right?
Correct.
Okay. So maybe then like this is a sort of, I would say, a soft constraint, right? Because there could be some finite number of users for whom the privacy is not assured.
Absolutely right. Yeah, that's this is one way of looking at the problem, and I was just looking at an asymptotic formulation. Then it's easy to define perfect privacy. I didn't go into the details of that. Sometimes people assume what you can do is that you can say that this is less than some epsilon, and call it epsilon privacy, or there are different other measures. It's not all mutual information, and as you absolutely said, it's possible that you can have finite number of users. Different users have different levels of privacy. It's all possible. I'm just trying to kind of provide the simplest kind of scenario, the cleanest and the easiest scenario.
Okay, thank you.
Sure. So as I said, this kind of approach has been studied. For example, this is one example of a potential result. You can think of, we have two operations for privacy, right? Obfuscation and anonymization. So the privacy depends on the level of obfuscation and anonymization. For example, in the case of IID, which is the easiest case, we can obtain this kind of simple graph. This y-axis shows the noise level. So there is a threshold. If your noise level is larger than something, then you have perfect privacy. And the same thing with anonymization, right? The level of anonymization is determined by the number of observations per anonymization mapping, right? How fast you're changing your anonymization mapping. And again, there is a threshold, below which you have perfect privacy. And then in this region, you have absolutely zero privacy. In the limit, as n goes to infinity, the adversary can completely identify the users and de-anonymize the data, okay? So that's a kind of a typical result that you can have. And again, our group and other groups have studied these kind of problems. This is kind of an example of some of the results that we have studied for different kind of contexts, assuming different models and so on. Okay, so that's kind of one approach to the problem. But there is a fundamental question here. What if the assumed model is not accurate in the first place, right? I said the data, for example, is Markov chain, right? Now, it's quite possible that the model that we assume is not accurate, right? And this is, in fact, for real data, this is quite possible, as I said, because in real life, things are changing, dynamics are changing, things are evolving, many things depend on each other. So we really have a fixed statistical model that we can kind of assume and then develop our privacy mechanism. So then what happens is that if you assume a model, for example, fixed model, Markov chain, and then develop this privacy mechanism, it turns out that this could be catastrophic to your privacy. We provide examples. I'm not going to go into the details of that. If you are interested, you can look at this paper. That if the model is not correct, then the adversary might be able to completely break the anonymity. You think you have perfect privacy. In real life, you have zero privacy. So this could be catastrophic. So the fundamental question that arises here is that, can we develop a model-free approach, right? Can we develop a approach to privacy that is kind of not based on any model? The user's data could be anything. We don't make any assumptions about the statistical model or anything. So that seems to be, maybe it's a difficult question, but we can make it easier. Let's think about this a little bit. One thing that comes to our mind is the following. If you think about it, many privacy attacks in real life, if you look at the papers and these privacy attacks, many of them are based on pattern matching, right? In this kind of context, of course, that I'm talking about, this sequence matching. So are based on pattern matching. So what do I mean by that? So for example, let's say you look at my personal data, right? My location data. I usually go from my office, right? Go to my home, and then take my kids to the ice rink, the hockey rink. So that's a very normal pattern for my data, right? I might go somewhere in the middle, right? Maybe buy something and so on. But what happens is that these locations A and B and C appear in my personal data, personal location data. Now, suppose that a potential adversary looks at a large number of sequences, and then there is only one person who is going to, this is me, going to locations A, B, and C, right? So what happens is that this adversary is able to identify me among the collection of this user very easily, because this is a unique pattern that I have. And that's what I mean by a pattern here in this kind of context. So a large number of privacy attacks are based on these kind of pattern matching attacks. And the question is that, can we develop a method to kind of protect against this kind of attacks? Okay, so to summarize, the point here is that users can be identified by their unique habitual patterns. So you can think of a user U that has this pattern. A pattern is just a sequence that appears as a subsequence of the user, right? So that's kind of the scenario we are considering. So the question is that we want to provide a privacy preserving mechanism, even if we do not know the exact statistical model, and essentially we assume nothing about the statistical model, and we still want to provide a privacy guarantee against these pattern matching attacks. So you see there is a trade-off here, right? We are assuming nothing. The good thing here is that we don't assume anything about the data, so that's great. However, we are protecting against a very particular kind of attack. It's not a mutual information kind of guarantee, which is very general, but it's a guarantee against a very particular attack. And at the end of the talk, I'm going to talk about how we can combine the two so that we get best of the both worlds. But at this point, we want to focus on this privacy against pattern matching attacks. So the main idea is actually very easy. The idea is very simple. If you think about it, what we're going to do, we're going to obfuscate in a way to maximize the number of patterns that exist in the data, right? So if you have a large number of users and you obfuscate the data, you perturb the data for each user, you do it in a way that you maximize the number of patterns. Now, if I am a particular user with a particular pattern, it's very likely that many other users have patterns similar to my pattern, and this way we can guarantee some sort of a privacy against this kind of attack. So that's kind of the main idea. So again, the model is the same. You obfuscate and you anonymize the data. There are n users. The only thing that we assume here, again, no model for the data. The only thing that we assume is that the alphabet size is R, right? For example, if it's location data, essentially you assume that you have R locations. So from 0 all the way to R-1 locations that users can be. So that's kind of the assumption here. Now, before we go any further, we need to define what do we mean by a pattern. So what's a pattern? So a pattern is essentially a sequence for any user of length L, a pattern of length L, and two conditions must be satisfied. First of all, this pattern must be a subsequence of the user's data, not necessarily consecutive, right? Like A and B and C, it might appear in my data, right? And they must appear, close in terms of time, right? The distance between them must not be very large, right? Essentially, we provide a kind of a threshold H, and we say the distance between these should be less than that H. So, for example, in this sequence below, 1, 6, 4 is a pattern for this user. Why? Because these locations or data point 1, 6, 4 appear in the same order, and the distance is not large. Essentially, if H, for example, is 3, the distance between them is less than 3. So we want to define it mathematically in a clear way so that we can kind of provide privacy guarantee and so on. So that's what we define as a pattern in this context. Okay. Now, so then how do we thwart pattern matching attacks? The main idea, as I said, we want to increase the number of patterns in the obfuscated data of users. So what we're going to use a concept of superstring. So what's a superstring? Well, let's consider a specific length. Let's say L is equal to 2. So we are considering the patterns of length only 1 and 2. So how many patterns can I have of length 2, right? If you, let's say the data is binary, right? So binary data. So, you know, essentially you can, you have 4 possible patterns, right? 0, 0, 0, 1, 1, 0, and 1, 1, right? Now, what's a superstring? Here is an example of a superstring, right? Why is it a superstring? Because it has all of these patterns as a substring, right? So it has 0, 0, it has 0, 1, it has 1, 0, and it has a 1, 1, right? As in a consecutive, in a contiguous way, right? So it has all of these. So this is a valid superstring for patterns of length 2. So that's the concept of a superstring. And we're going to use this superstring in our obfuscation. So mathematically, we define a sequence. It is an RL superstring. So R, remember, is the alphabet size. L is the length, right? Length of this kind of patterns that you're considering. If it contains all the possible length L strings on a size R alphabet, as is contiguous substrings, right? So how can you make superstrings? There are many, you know, in fact, infinitely many superstrings of different length. The easiest way, and which I call a naive way, is the following. So let's say, you know, R is equal to 2. So binary data, length is equal to 3. So how many patterns you could have? 0, 0, 0, 0, 1, all the way to 1, 1, 1, right? So there are 8 possible patterns. The easiest way, the naive way of making these superstrings is that you just kind of put them next to each other and call the entire thing, you know, your superstring. Of course, this is not a very efficient way of doing it. You know, you can make it much shorter in length, but you know, it's by our definition is a superstring, right? Now, if you think about it, for any construction of these superstrings, there are many ways you can, many different superstrings. For example, in this case, you know, how many different patterns do I have? In general, I have R to the power of L patterns, right? And by reordering them, I think you can have R to the power of L factorial different superstrings, right? Just by, you know, different permutations of them. So essentially, you can have a large number of superstrings that you can use in your anonymization techniques. Now, how are you going to use this superstring to obfuscate the data? So suppose that I have a mechanism to create a random superstring. So here's what we're going to do. For any user U, we are going to choose a superstring randomly, right? Let's call it a U of 1, a U of 2, and so on. Now, let's say this is the data of the user, right? XU of 1, XU of 2, and so on, you know, time 1, time 2, time 3, and so on. And each time you toss a coin, with a large probability, you don't do anything, right? You don't obfuscate the data. Remember, we don't want to distort the data too much because that hurts our utility. Now, once in a while, maybe probably 5%, we need to distort the data. So what we're going to do, we're going to replace the data point with a value from the superstring. So XU of 1, XU of 2, and then we put the first value in the here and continue. Then we don't do any obfuscation and so on. And next time you need to obfuscate, again, you take the second value from the superstring. So essentially, these values from the superstring are going to be injected whenever you need to do obfuscation. And it's easy to see what's happening here, right? We are injecting these values from the superstring in the sequence of the users. And because there is a lot of patterns, by definition, the superstring has all the patterns in it. Then each sequence contains a large number of patterns. So that's kind of the way we are achieving privacy for this specific case. So the anonymization is the same as before. Now, what kind of assumptions do we have here? The adversary knows all the mechanism, everything about the mechanism. The only thing that the adversary doesn't know is the realizations of the randomness in our method. So for example, you may remember we choose a superstring totally at random. So the adversary doesn't know which superstring is used for a particular user. Oops, sorry. Okay. So the adversary doesn't know which superstring we are using for each user. Remember, we are tossing a coin to decide, do we want to obfuscate? So the adversary doesn't know which values are being obfuscated. And finally, The anonymization also done randomly. It's a random permutation, and the adversary doesn't know. So anything that is random, the adversary doesn't know. But the mechanism, the adversary knows. So now, what kind of privacy guarantee can we obtain in this kind of context? We call it epsilon privacy. Let's consider the naive superstring for now, the simple superstring. So, and let's fix the user V, right? And suppose that there is a pattern that the adversary knows about this user, right? It could be anything, any sequence of length L. We say that this user has epsilon privacy if for any other user, the probability that user U has the same pattern is at least epsilon. So what does this mean? You know, if there are n users, there are n-1 other users than this user V. If each of them has this pattern with probability epsilon, then on average, this many users, n-1 times epsilon, other users have the same pattern. And if this number is large, then it's a good thing I have privacy because there's a large number of other users that have the same pattern, and the adversary won't be able to identify me by doing this pattern matching. Okay, so let's consider the naive superstring. As I said, what kind of privacy can we obtain? The length of the superstring in this case is L times R to the L, and it turns out that we can achieve. This PB, this is just my epsilon, right? Probability of the user U have my pattern, right? It's just the probability that a particular user has my pattern. And we want to obtain a bound on this probability of BU. We can also easily show that the optimal superstring has length this is the length of the optimal superstring. And again, there is a large number of superstring with this length. And this gives us a better privacy because the patterns are more packed together in a more efficient way, and it's more likely that we inject these patterns when we are doing obfuscation. Okay, so this is the first result. This is using a naive superstring. So with our definition, this is essentially my epsilon, right? I have a bound on the probability that any other user has my pattern, right? For a fixed any pattern, this bound applies if you are using the naive superstring. Now, how do we prove this? If you think about it, we need to, what kind of probability do we need to find here? Consider a fixed pattern, right? And let's say one user have this pattern ABC of length 3 or something, and consider a user U that this is the sequence for user U, and we are obfuscating the data. At some points, we are injecting data from the superstring, right? Now, remember, the superstring is obtained randomly, which means that, first of all, it's a superstring. So at some place, it contains this pattern, right? Somewhere, these patterns appear in the superstring. Now, the location of that is random, right? If it appears earlier, it's more likely that this user have this pattern. So we can compute that probability. The other probability that we need to take into account is that whenever this pattern appear, these data points need to be close to each other, right? Remember, we are obfuscating with the probability. So there is a chance that these are close to each other. Now, it turns out these two events are not independent, but you can do a trick and define a slightly different version of them that can become independent, and then you can kind of compute those probabilities and kind of obtain a bound on this privacy guarantee. So I'm not going to go into the kind of more detail on that. Now, that was the true for the, this bound is true for a naive superstring. Now, you can repeat a similar argument for the case that you have, you are using the optimal superstring with the shortest possible length. You obtain a similar bound, but it's a better bound in terms of privacy guarantee because you are doing it much more efficiently. But the proof and kind of analysis is very similar. Okay, and we can check these bounds with a realistic data, some real database. We checked it, and these are the epsilon and epsilon prime that we obtain. You see that with the optimal superstring, you get a better, much better privacy guarantee. So, and so on. So these probabilities go significantly higher when you are using the optimal superstring. So that's kind of one way, the initial approach that we had to this problem. Now, these results that I showed are quite, are not asymptotic. So they are true for any n, for any values of n, length L, and so on, ADP, and so on. But it's interesting to see what happens asymptotically, right? And there are many different versions of asymptotic version of this. This is one of them. The good thing about this, we can see the fundamental trade-offs here. The interesting point here, I want to point out here two things. First of all, probability of obfuscation, if you note, is in the order of 1 over n to the power of some positive value. This is good. Why? Because as n goes to infinity, this thing is going to 0, right? So the fraction of values that we are changing, obfuscating, is going to 0, which is a good thing, right? We are not distorting the data too much. Another good thing here is that the obfuscation probability is in this form. What does it mean? If you think about it, I have n user or n minus 1 other users, right? And all users, the probability that they have my pattern is this, right? Something like this. So essentially is n to the order of n to the power of beta, which beta is positive. So, the average number of users that have my pattern is given by this order, which is going to infinity. So essentially what it means is that on average, a large number of users have my pattern. So it's a good thing. So it's a good guarantee for privacy. Again, I want to emphasize it's a privacy against a very particular kind of attack. It's not a mutual information type attack, privacy guarantee, but it's a privacy against this kind of attack. This is another topic extension that I don't want to go through it, but just mention that if you are interested in, we have it in our paper. We can, so far we don't look at the data at all, the actual data. When we are doing obfuscation, we don't make any assumption, any models. We don't look at the data. We just obfuscate using this mechanism that we explained. Now, for some applications, specifically if they are not real time and so on, you can look at the data and use the data to do this obfuscation in a more optimal way. How? For example, if this is my data, when I'm obfuscating, I can look at the data and use this value in a more efficient way to maximize the number of patterns, right? For example, if a particular pattern is already appeared in the sequence, I don't need to recreate it. So in some sense, I can count the patterns and try to optimally obfuscate. Of course, you have to be careful because you want to have an efficient way. So it turns out you can do it efficiently, these pattern countings, and you can obtain a better privacy guarantee if you are allowed to use the data, data-dependent obfuscation. Of course, the complexity is more than previous, and you are using your data, but it's for some applications, this is possible. So I'm not going to go into that direction, but for the rest of the talk, I want to talk about at least what I think is an interesting extension that we have been working on, and this is the constraint obfuscation. Right? So what do I mean by that? So far, I assume that the data could be anything, right? There is no constraint on the data, just some values from some alphabets. But in many real life applications, the reality, there are constraints on the data. For example, if this is location data, if the frequency of reporting is high, locations should be close to each other, right? Let's say I am reporting my location to some application. I go from here, then I go here. Now, suppose that I need to obfuscate, right? With probability 5%, I need to obfuscate. Suddenly, the value becomes this. So essentially, the adversary looks at the data, sees that I went from here to here to here, and then suddenly I jumped here. Now, these distances might be small, let's say less than 1 mile, and suddenly I jumped 10 miles, right? So that clearly provides information to the adversary that this is not a real value. This is a fake value. It's the result of obfuscation. So we are leaking this information. So for this type of application, we need to preserve the continuity of the obfuscated data. Otherwise, we won't be able to achieve any sort of privacy because the adversary can easily identify the obfuscated values. So how can we approach this problem? Again, we don't want to make any assumption, but we just want to make the this continuity assumption, right? So the way we model it is the following. We assume a general graph GVE that shows we can think of it as a proximity of the data, right? So essentially, if one data point, if you can think of it as location, but it applies to any continuous data or any structured data. If I am at location I, my next location is one of the neighbors in the graph of this location, right? That's the only constraint that we assume. So essentially, users are traveling through this graph. It's not necessarily a Markov chain on this graph, right? Your next move could depend on all your history or something like that. All we are assuming is that this data of the users and the obfuscated value, of course, must follow this graph, right? This way, we are ensuring that we are preserving this structure of the data, and then we want to obfuscate to preserve privacy against these pattern matching attacks. So how can we do this? And of course, the users can have a subset of this graph, right? But this general graph is the biggest one. So the data of the users are follow this graph, right? Okay. So it turns out this problem becomes more challenging. Why? Let's see. Suppose that this green path shows the actual location data. So 1, 2, 3, 4, 5. Okay. So now suppose that I'm tossing a coin. I don't obfuscate. I'm come here. And then I come here. And now I need to obfuscate, right? Now I cannot obfuscate to this value. Why? Because that would mean that the user jumped from this 3 to this value here, right? Let's call this 4 prime. I cannot do this because this edge is not in the graph, right? So I have to be careful. If I want to obfuscate at this point, this obfuscation should be one of the neighbors of 3. It could be 2 or could be, for example, here, this 4 prime, right? So I need to obfuscate to 4 prime. Now, the problem could get more complicated. Let's say the user then goes to location 5. Now, I have to obfuscate because I cannot say the user jumped from 4 prime to 5, right? Maybe I choose this as 5 prime. This is the reported data. Now, you see there is a problem. First of all, I am obfuscating these values again. Remember, we don't want to obfuscate too many values. More importantly, this distance, right, between these two nodes could become large. And again, the distance could be very important in terms of the utility of the application. Let's think about, if you are using an application such as Yelp, right? I want the application to recommend restaurants near me, right? However, if you, for example, if you obfuscated your location to 100 meters away, that's okay. Again, it's close to restaurants close to this location are the same as restaurants close to your original location. However, if you report a location here, you get restaurants near that location, which is not good. So we have to be careful and we need to deal with these kind of challenges. So that's what we want to consider in this part of the problem. So we need to make some sort of regularity assumptions. Again, we don't want to make any particular assumption, but we need some mild assumptions to be able to move forward. So what are kind of assumptions? For example, we say that if some location or some data location I belongs to the vertex of some user U, then the long-term probability of that location cannot be 0, right? Otherwise, we don't include I in the kind of the vertices of that user, right? The locations of those users. So kind of simple regularity assumptions, nothing very particular. So we assume some mild regularity assumptions. And then we also focus on consecutive patterns. What do I mean by, because we are talking about the proximity of the locations, we consider only like consecutive patterns, A from B to C, and the adversary is trying to use these kind of patterns to identify the data. Okay, so what kind of requirements do we need to have? Excuse me. Sorry. Oh, yeah, this is my fourth or fifth talk today, meetings and so on. So I need a little bit of water. So anyway, so these are the requirements that we need to satisfy. For the obfuscated data, we need to have the obfuscated data to be a valid data set, right? Z is the obfuscated data. So ZU of K and ZU of K plus 1 must belong to the edges of the graph, which means that the adversary cannot easily identify the obfuscated values. So the next condition that we need to satisfy is that the noise level must be small, right? Essentially, the fraction of values that we are changing should not be very large. Next assumption or requirement is that the distance between the real data and the reported data must not be large. It must be less than some threshold. And finally, this is our epsilon thing, right? For any pattern, a large number of other users must have the same pattern. So can we achieve all of these requirements? It turns out we can, and we can achieve it using an algorithm that we propose, and we call it Obfuscate-Return algorithm. It's based on two simple operations, obfuscation and return, two simple fundamental operations that we repeat them in a specific fashion to obtain privacy. So obfuscation operation is very simple. Essentially, it tells you that if you are reporting this value ZU of K minus 1, with probability 1 minus P, maybe with probability 95%, you don't do anything, you don't obfuscate, you report the real data. With probability 5%, for example, you choose one of the random neighbors of previous value, right? And these are neighbors, so you don't break your constraint to be on the graph. The next operation is a return operation. And the return operation is the following. Suppose that this is, again, the real data, XU of K minus 1, XU of K, right? And this is your current reported value. It could be the same as XU of K, but it could be different. What it says is that you choose one of the neighbors of ZU of K minus 1, but you choose the neighbor with the minimum distance to the actual value of XU of K. And by the distance, I mean the distance on the graph in the sense of the shortest path on the graph. So these are two simple operations that we're going to use in this Obfuscate-Return algorithm. Now, it turns out that this is the specific way you are using this operation, but the idea is actually pretty simple. I can explain it using this picture. So suppose that this is the green path is actually your original path, right? The user goes from location 1 to location 2, 3, 4, 5, and 6. So at each point you toss a coin, right? You don't obfuscate at 1, at 2, at 3, and maybe at 4 you need to obfuscate. So what you're going to do, you're going to choose one of the neighbors of 3 at random. So you call this 4 prime. Instead of 4, you report 4 prime. Now, starting this point, then you obfuscate, you run obfuscating for L minus 1 points. Remember, L is the maximum length of the pattern that you are trying to protect against. So in this case, L equals 4. So we obfuscate for 4 values, 3 values essentially, L minus 1. And then from then you do the return operation. Try to return to the original, to the path. And of course, you are doing it in multiple steps. So this is kind of the idea of the Obfuscate-Return algorithm. And again, the details is provided here. Now, it turns out that if you do this, then you can achieve those privacy guarantees that we mentioned. You can, first of all, have a probability of obfuscation that is, again, in the order of 1 over n to the power of theta, right? Which means that it's going to 0 as n goes to infinity, right? The maximum distance is small, is bounded. So whenever you are reporting the data, the distance to the actual data is not large. The noise level, again, is in the order of something over n to the power of something, positive value, again, goes to 0. And most importantly, the probability of any pattern is given by in this format. So because you have n in the order of n users, then the average number of users with any pattern is in the order of n to the power of 1 minus theta, right? So the average number of users with a particular pattern, goes to the infinity. Okay, and of course, these values is important, what this theta is and so on, which is given by the parameters in the theorem. Okay, so what's the proof idea? The idea is the following. Suppose that this green is my original path, right? So what we're going to do, how do you obfuscate? At some point, you deviate from the path for some time and then go back, right? So we prove two things. First of all, we prove that the length of this deviation turns out not to be large, right? And also the number of them, we bound the number of them. So, and from that, it's easy to show that the fraction of values that you're changing is not large. So essentially, most values, you are not doing any obfuscation. That's the first thing. Next, again, it's not difficult to show that the maximum distance is going to be in the middle of this path. And this maximum distance, again, is bounded by 2L minus 1. So it's not large. So again, you are not reporting for locations to your actual data, and so on. So this is kind of the main idea of the proof. It turns out that, as I said, all of these four conditions can be satisfied. You are always reporting values on the graph, right? So you are not, jumping from location to locations. The noise level goes to 0. The distance is limited, and the probability of having a certain pattern is going to be large enough. So that's kind of the achievement that we obtain in this kind of context. So I want to kind of finish the talk by talking about combining the two methods that we talked. Remember at the beginning of the talk, I mentioned that there is a lot of literature on model-based approaches, right? Now, here we talked about model-free approach. So how do we use them? Now, one way to do them is that to combine them, right? If you think about it, usually the noise level, is very small fraction anyway, at least asymptotically, right? It could be epsilon, or asymptotically, maybe you are changing only one fraction, 1 over the square root of n, right? Now, if this is a noise level, and this is your noise level for the model free, even if you combine them asymptotically, at least, you get the same order, right? So when the noise levels are small, combining them is very, you pay a very small price. But the good thing is that doing this way, you are protecting yourself against, pattern matching attacks. And think about it. In real life, we might not know the model exactly, but we have some idea about the model, some guess. So we can design a model-based approach and then combine it with the model-free approach. And if our model is correct, that's perfect. We get the perfect privacy in the sense of mutual information, which is awesome. However, if you're wrong, at least you have protection against pattern matching attacks. So you can kind of combine the two methods in this fashion. And that's kind of the end of my talk. Thank you very much for your attention. I see that my kids are home, so it seems that I ended the talk right on time.
Thank you very much, Hossein. Yeah, it seems that was a good timing.